Today what we're going to do is we're going to show that Turing machines are closed under union. Now what that means is if we have some language A, which is inside of sigma 0, and some language B that is inside of sigma 0, then A union B is also inside of sigma 0 for all A and B. Now recall that we already did something like this for DFAs and context-free grammars. So with context-free grammars, it was easy to just produce a new machine, let's call it CS. So this is the C grammar, and its start symbol would just go to either the A start symbol or the B start symbol. Now with DFAs what we did, actually let's do NFAs first. With NFAs what we did is we just made a new machine who its start state had an epsilon transition and another epsilon transition. In this case it went to the A machine, and in this case it went to the B machine, and then had an epsilon transition out to an accepting state. And then we also previously did something with DFAs where we constructed a new machine that was called QC, and its states were just pairs of QA and QB, and its delta function was something like this, where we wrote delta of Q little a, Q little b, and then the character was given C, would just be equal to a pair of calling delta, this is delta C, delta for A on QA and the character C, as well as calling delta B on QB and the character C. So in each one of the previous models that we've done, we've proved the same thing, that you can take something that's in the same category, another thing that's in the same category, and get something that is the combined version. Now what we'd like to do is do the same thing with Turing machines. Now recall that Turing machines are described by Q, sigma, gamma, delta, which goes from Q cross gamma, arrow Q cross gamma cross LR, and then we also have QA and QR, and there's also Q0. Okay, so we have all of those things. That's what a Turing machine is. Now, it's not obvious how we can apply the same idea as any of these models. For instance, we can't do the context-free grammar thing where union is just built into the language because it's not built in, not built into the language, built into the specification, because union is not just built into Turing machines, so we can't do that. We don't have non-determinism, so we can't use the NFA idea, and the DFA idea is close, but the problem with the DFA idea is that Turing machines, as they're running, they may need to modify their tape as their operation. So you should really think about Turing machines as being like little tiny C programs, okay? And what the tape is simultaneously their input and the memory that they use during the computation. So imagine that I had one C program that was going to look at a file, and let's say it was going to search through that file for all instances of the phrase Mr. Darcy. And then there's another program, and this one is going to take a file, and it's going to look through all instances of the word Aegon Targaryen. Okay, so these two programs are very similar to one another. They both have the same sorts of answers, but of course they're going to use memory differently. And when we compile them, the Mr. Darcy program, maybe it's going to store the count of how many times it found Mr. Darcy in address 8. And then maybe the Aegon Targaryen program, it's also going to store something in cell 8. And if they both try to use the same cell of memory for different kinds of information, then the programs are going to be broken and they're not going to run correctly. So what we need to do then, if we want to combine them together, we can't just combine them together on the basis of their states. We also have to make it so that they can have memory that won't overlap with one another. And so what we'll do is we're going to create a new kind of Turing machine that's called a multi-tape Turing machine. Multiple tape Turing machine. And the idea behind the multi-tape Turing machine is that its delta function will be different. Its delta function will go Q, that's the state that it's in, then it will go gamma to the K, where K is how many different tapes there are. And then its result will be the new state, Q, and then also what it's going to do to each tape. And so here we're going to have K different instances of what will get written and what direction will go in. The idea behind this is that it's as if the single tape is connected, the single control unit is connected to two different tapes and it can do different things with each one. Okay, now how do we then actually make use of this? Well, first of all, we should write down the rules to describe how it works. And what I'm going to do is I'm going to write down the rule. I'm going to give you just an example of how the rules work, focused on K equals 2. So imagine that K equals 2. In that case, we have to say what a configuration looks like. And here's what I'm going to say a configuration looks like. I'm going to say the configuration looks like this, where we have a state, Qi, and then we have the character, the string that's to the left of tape 1, the string that's to the right of tape 1, the string that's to the left of tape 2, and the string that's to the right of tape 2. So for example, an example configuration might be something like carry, and then it would have like 0, 1, 1, and then after this it would have like 0, 0, 1, 1, 1, 0. Okay, so in this case, the machine has moved to the right. It's moved to the right 3 on the first tape, and then there's 3 more things ahead of it, and then there's 3 things over there. Okay, so now here's an example rule. Imagine that we call the delta function, and we're in state Qi, and then we're going to be looking at, let's say we're going to look at A on the first tape, and then alpha on the second tape. And then what's going to come back is going to be a new state, Qj, and let's just suppose that we get B and a left for the first tape, and then we get beta and right on the second tape. What would this situation describe? This would mean that we're in a configuration where Qi is looking at an A and an alpha. All right? Now, what's after the A? Let's say that V is after the A and Y is after the alpha. And let's say that X is before the alpha and then UC is before the A. In that case, we're going to change to a new configuration where U is to the left, we're in state Qj, and then ahead of us is CBV, because we moved to the left, which means that we changed that A to a B, and then we moved one left. And then let's suppose that down here we have X and beta, and then Y. So we would have 4 more rules like this. One for when they both go left, one for when they both go right, and one for when they go right and left. And so we could then describe the exact, not the exact same, but an isomorphic configuration transition system for our multi-tape Turing machines. Now, what could we then do with this? Well, what we'll be able to do is we'll be able to build a proof of the union. So here's how we'll implement union. So the idea behind union is that we're going to take A and B and produce a new machine that's A union B. So let's suppose that our Turing machine for A, so we'll say TMTA, is equal to QA sigma gamma A Q0A delta A and QAA and QRA, where delta A's type is that it takes a QA and a gamma A and returns a QA, a gamma A, and a left or right. Okay. Now there's also going to be another Turing machine that we're provided with that's for B, that has the same sorts of things. It's got QB, sigma, gamma b, q0b, delta b, qab, and qrb, where delta b's type is qb, gamma b, qb cross gamma b cross LR, right? And we're going to return a multi-tape Turing machine, TC. Now let's say what all its pieces are. So its states, QC, what are we going to say that they are? Well, how is this going to work? Essentially what's going to happen is that we're going to assume that the input comes in, and let's just assume that the input is on both tapes. That's just convenient. So the input is duplicated on all of the tapes. So then what we're going to do is we're just going to run each machine. Okay, so our states are going to be pairs of QA and QB, plus there's going to be two more things, which is our accept and our reject states, because they have to be separate. Now, gamma is going to be, so what we could do is we could say that there's a different gamma for every tape, and that would be easy, because then we would just say that gamma A is for one tape and gamma B is for the other one. That's probably the simplest thing to do. But the way that I wrote the definition of multi-tape Turing machines, there's just one gamma set, and we write the same thing on both. So in that case, what we'll do is we'll just union the two of them. We'll just say gamma A union gamma B. Okay, then we have to say what Q0 is. So we'll say that Q0 is that we're going to start in Q0A, comma, Q0B. So we start in the two different machines. All right, then what are we going to do? Well, now we have to write the delta function. So here's the delta function. We're going to say that delta of QA, comma, QB, all right, when we're given a character CA and CB, because remember, the delta function is going to get a state, and then it's going to get a tuple of all of the different tape readings. Okay, so now what we need to do is we need to return a new state to go into. So we need to return a new state, which we'll call QC. And then we also need to return what we want to write to the left tape. So we'll call that C prime A. And then what direction we want to go on the left tape, so we'll call that DA. Then we also want to write down what we're going to write on the right tape, which we'll call C prime B, and then DB. What are these things? Well, C prime A, DA is just going to equal delta A called with QA, CA. Sorry, made a mistake. We need to just fudge this a little bit. So I'll just rewrite the whole thing. Okay, where QA prime, CA prime, and DA, that's going to be equal to delta A of QA, CA, and then QB prime, CB prime, and DB are going to be equal to delta B of QB, CB, and then QC, the new state, is just going to be QA prime and QB prime. Okay, we now need to do just one last thing, which is that we need to write down how to get to the accept and reject states. And it's quite straightforward how to do this. What we do is we'll say that delta of QAA and then anything and then anything and anything is just equal to QA, and then we don't care what these are. So if we get to an accept state on the A machine, we say yes. If we get to the, if we don't care what happens on the A machine, but if we get to the accept state on the B machine, and we don't care what these say, then we also go to the accept state. And if we get to the reject state in both, then in that case, we go to the reject state because it said no to both. Now there's a little bit of tweaking that we need to do because technically you can't call the delta function on the reject state. So if one of them gets to the reject state, we have to ignore that. And if the other one gets to the reject state, we have to ignore that one. And if we, Now, what this shows is how we can use multi-tape Turing machines to show that the Turing machines are closed under union. We can also get intersection by just changing these rules down here, by just saying you have to get to both accept states before saying yes, and if you get to either reject, then you say no. Okay, so that would be the sort of like the dual of this gets us intersection, but all the other parts stay the same. Now, however, this is only useful for showing that Turing machines are closed under union if we can show that, actually, hold on, I'll hold off just 1 second. What I've just shown shows that sigma 0 is closed under union. Under union and intersection, or at least it will attempt to do that. Because we are assuming that each one of these Turing machines is a decider, which means that it never loops forever. But now what if, instead, one of them looped forever? What about sigma 1? Would it still work? Well, remember, if something is in sigma 1, that means it may loop forever if it would otherwise say no. So something is not going to say yes, and so it'll loop forever instead. Well, in this case, since we're running them in parallel, we take a step of both simultaneously. If one of them is eventually going to say yes, then whichever one says yes will say yes first, and then we will say yes. So that means that if one of the two machines, A or B, goes into an infinite loop, it won't affect us. It won't matter because we're running them in parallel. And so this means that sigma 0, the decidable languages, and sigma 1, the recognizable languages, are both closed under union. All right, but all this is only relevant if we can show that multi-tape Turing machines are equivalent to normal Turing machines, i.e. whether we can compile a multi-tape Turing machine to a normal Turing machine. Now the way that we're going to do this is we're going to use that bisimulation concept. So imagine that we have some configuration like UCQIAV and X alpha Y, and we want to turn this into UQJ CBV X beta Y. Okay? Now, and let's suppose that there's, let's just clarify just one thing a little bit. Let's just suppose that there's alpha and then gamma Y. So then we have gamma Y here. Okay, now clearly this kind of configuration doesn't make any sense in terms of normal Turing machines, because normal Turing machines only have one tape, not multiple. So what we need to do is figure out a way to turn a configuration like this into a configuration on normal Turing machines. So as an analogy, imagine that you wanted to read two books. So you want to read Pride and Prejudice, and you want to read Fire and Blood. Okay, so you want to read those two books. So you want to read Pride and Prejudice and Fire and Blood. Now, one way that you could do that is that you could like staple the books together. But imagine that you don't have a bookmark, and you just have to have one page open at a time. That's kind of how a Turing machine works, right? In a Turing machine, you can have just one cell that you're looking at, that's where the tape head is, and there's stuff before it and there's stuff after it. That's what this means right here. This means that you're currently opening the book up, and in this case, we're opening up two books. We're opening up Pride and Prejudice, and we're on page A, and we're opening up Fire and Blood, and we're on page alpha. And then because of what we read in Pride and Prejudice, we decide that we want to go back one page and look at page C, but because of Fire and Blood, we want to go forward and look at page gamma. The thing, though, is that in this brave new world of normal Turing machines, we only have a single book. So how can we do this? How can we make it so that we can read two books simultaneously while only having the page open to one thing at a time? Well, I kind of gave it away a little bit, which is that you can use a bookmark. So what we could do is we could dog-ear the page alpha. And if we dog-eared the page alpha, then we would know that later on, what we could do is we could look at page A and then remember that we're looking at page A, and then we could go forward and then we could find page alpha, which we dog-eared before, and then look at that. So the way that we do this is we say that we're going to turn this configuration into the following. We're going to put the head at the very top, and we're going to be in state QI. Then what we're going to do is we're going to just lay out the entire book. So it'll be U, C, A, and V. But then what we're going to do is we're going to dog-ear A, and we're going to put a little caret on top of it. That's going to indicate the dog-earing. And so what does this really mean? This means that gamma is going to be equal to 0, 1 cross gamma, where the zeros are not dog-eared and the ones are dog-eared. And then what we're going to do is we're going to have a special symbol, which we're going to write as a hash. So that's just another thing that we put inside of gamma. So this is gamma prime, is going to have 0, 1 cross gamma, and then it's also going to have hash. And this hash is going to be basically the binding between the books, the separation between the two books. And then after that, we'll have the second book, Fire and Blood. It'll have the X, the alpha, the gamma, and the Y, and that alpha is dog-eared. Okay? Then we're going to eventually run, and what we're going to get back is we're going to get back a QJ, where we have U, C, and then that's where the dog-ear is, B, V, and then we have the hash, and then we have X, beta, the gamma with a dog-ear on it, and then Y. So now what we need to do is we need to explain how to turn this tape right here into that tape. Now there are a ton of different things that we need to do. The first thing that we need to do is we need to scan through and find the first thing that's been dog-eared. And then we'll know that, okay, now we were looking at an A. So the idea is that we basically we'll have a state that's called QI, we're on the left-hand side. And then from QI on the left-hand side, we're going to scan forward until we find the dog-eared page. And that's going to bring us to QI, I saw an A. And then what we're going to do is we're going to go until we find the second dog-eared page, and we're going to call that QI A alpha. And that means that I saw an A and I saw an alpha. Now at this point, what we can do is we can go run the delta function and figure out what we're supposed to do. And the thing is that when we know what we're supposed to do, we'll go to a state that we'll call we'll call it QJ, because that's the state that we're going into. And then it'll be, B and left, and beta and right. So we'll record inside of the states what it is that we're supposed to be doing. Well, now we know that what we're supposed to do in the beta right state is that we're supposed to write a beta and move to the right. And then after we do that, then we'll go into the QJ and the B left state. And then we'll go back to the left until we find the thing that we dog-eared before. Say, aha, what I need to do is change that into a B and then move left, i.e. I need to turn A hat into B, move left, and change whatever is there into that thing with a hat on it. And then at that point, what I'm going to do is I'm going to go to the QJ, beginning state, where what my job is to keep going left until I hit the blank. And then after that, I'll go down to there. So there's this very complicated network of stuff that we need to do. We need to scan to the left, find something. Scan to the right, find the thing on the left. Keep scanning, find the next thing. Look up what we're supposed to do, then start doing it. And then once we do it on the right-hand side, then we move back and we do it on the left-hand side, and then we go to the beginning, and then we go back to the beginning, and then we get back to this spot. And even this network of stuff is actually more complicated than what I described, because there's this weird problem, which is that, well, where did the blanks come from? Because remember, each tape is supposed to be infinitely long, but clearly they're not infinitely long in these 2 points because the hash is separating them. So what do we do about that? Basically, the idea is that if you ever get to the hash, and like if you're ever at the last character and you want to move to the right, then you have to like stop and then push everything over one and stick a blank right there. And then similarly, if you're ever at the first character on the second string and you want to move left, you have to stop, copy everything over, and then put a blank there. So this is a very complicated, tedious thing to do, but I hope that you can imagine how you would construct a delta function like that would actually do this. And it's sort of within the realm of possibility. And notice that what I've described only works for 2 tapes, but clearly a elaboration of this could exist for an arbitrary number of tapes. Or what you could do is you could just combine the 2 tapes, combine the tapes over and over again into multiple. So for instance, suppose that you wanted to have a machine that had 4 tapes, A, B, C, and D. What you would do is you would combine C and D into 1 tape, and then you would combine B and E into 1 tape, and then you would combine A and F into 1 tape, and then now you have 1 tape that has 2 things in it, where the second one has 2 things, where the second one has 2 things, and then there you go. Okay, so if you can combine 2 tapes together, then you can combine an arbitrary number of them together. You could even potentially do it more efficiently, like you could combine A and B together, C and D, and then you could combine those together. Okay, so there's a number of strategies that you could do to efficiently produce multi-tape Turing machines. All right, so we did it. Now, from this point forward, we're going to assume that we can trivially have multiple tapes whenever we need to with Turing machines, and we know now that sigma 0 and sigma 1 are closed under union. All right, see you next time.